Oklahoma State University and is a specialist to study the evolution of stress and strain in the electrode materials during the battery operation. Omer, without any delay, please proceed.
Can you see my screen, Rosie?
Yeah, there is.
All right. Good morning and good afternoon, everyone. Thanks so much for the invitation, first of all. Today, I'm going to talk about the electrochemical stress and strains in the cathode electrodes for the alkali-ion batteries, which I'm going to talk about a little bit lithium-ion and moving forward to sodium-ion, and hopefully, if the time allows, a little bit about the potassium-ion batteries. First of all, just to acknowledge our group members. So our group is established in 2018 fall. We are just 2 years old group. Currently we have 3 graduate students and 1 undergrad working with us. And this work, I'm going to talk a little bit about my previous work from the IUC and then how we evolve it to sodium and potassium battery study here. And with this, also I would like to thank you, the collaborators on various projects and funding agencies to supporting us on this journey. The outline of this talk is the first, I'm going to spend some time about the background in mechanical deformations. In particular, I'll talk about the stress and strains in graphite and some new studies by the Dr. McCovell group for the alkali-ion batteries, and talk about our techniques, how we really measure stress and strain. And in the next, I'll present you the stress and strain evolution in lithium-ion cathodes, in particular lithium manganese oxide and lithium iron phosphate. And from there, you're going to take it and move it to the sodium-ion batteries and explore the chemomechanical response of the iron phosphate upon lithium and sodium intercalation. And we'll look at the rate dependence of this lithium and sodium intercalation effect on the mechanics. And finally, if time allows, I'll present you the potassium intercalation results in the iron phosphate too. So all of us are very familiar here, but let's just take a seat back and remember there are 3 major components for the degradation in general for the lithium-ion batteries that also applies for sodium and potassium-ion batteries. The first one is the SEI growth. Dr. Pellet is here as he described the name of it. The SEI can consume the capacity and also diminish the surface kinetics of the electrodes. The another problem is, depending on the cathode material, is the dissolution. If you are using lithium manganese oxide, for example, there is a manganese solution problem. When manganese dissolves, it penetrates and reaches the anode surface and decomposes there. So also causes the extra SEI formation on the anode surface. A similar behavior also observed in the sulfur cathodes. The third one is the particle fracturing or mechanical instabilities. In this case, the electrodes are breathing lithium, sodium, or potassium, where they inevitably have the volumetric expansion and associated stress generation in the material. If you look at this figure here, courtesy to Dr. Elizabeth Jones, she took it almost 5 years ago. What you are seeing is the expansions and shrinkage of the graphite electrode during lithium insertion and removal. So these insertions inevitably, as I mentioned, cause the expansion in the material, but in the real environments, your electrodes are constrained. So this expansion introduced stress generation, and also there is the internal pressure on the electrodes. What happens is, in this figure, where the left one is a pristine lithium manganese oxide, and the right one is the after 50 cycles at relatively little higher scan rates, you can observe cracking. When cracking forms, it generates isolated and inactive particles. It's one reason the capacity is reducing. Also, it increases the surface area, where the other 2 factors, which are the SEI formation or solution, also intensify, that further escalates the capacity loss in these materials. So these stress and strains previously studied by various groups, especially Brown University and also URUC. In this case, I'm showing you the response of the graphite electrodes during lithium intercalation. So first of all, Here, the first one is current, second one is stress, and the third one is strain. And the color marks here demonstrates the phase transformations in the graphites upon the formation of the lithium graphitic compounds. As the lithium starts to intercalate, the current decreases and has the unique peaks associated with the changes in the structure, and that induces the compressive stress, or since the lithium ions are inserted, there is an expansion in the electrodes. During the anodic scan, this time the lithiums are removed, therefore there is a sharp reduction in the strain that also associates with the tensile stress growth in the material. The one thing you might realize here, the stress and strain is not linear with the voltage. There is localized changes in both stress and strain. So what they did is they take the derivative of the stress and strain with potential, and they observe that there is the large amount of stress rates just beginning of the initiation of the lithium insertion to graphites. And in the later stages, there's a strain derivative that correlates well with the phase transformations. The way they describe this, they hypothesize the stress comes from the kinetic limited diffusion on the surface, and later, as the lithium ions are inserted to the layer spacing between the graphitic components, it causes the angstrom scale expansion, which can be observed as the microscale changes in the strain rates. The other interesting study was done by the McDowell group. In this case, they look at the iron sulfur anodes. So here, the top figures are the pristine crystals. They use their Institute TM study for this. The crystals are about 50 nanometer, and they look at what happens after lithium, sodium, and potassium intercalation into these anodes. In general concept, we expect that the larger ions, such as sodium and potassium, will induce much greater volumetric expansions, and this great volume expansion should drive the mechanical instability in these electrodes. On the other hand, what they observe is the expansions upon lithiation was smaller than potassium and sodium intercalation. However, lithium insertion into these particular electrodes caused fracturing. And later, they did the finite element simulation to look at the concentration gradients at the edges. And what they observe is there is a sharp concentration gradient change at the edges during lithiation, but concentration is much more uniform during sodium and potassium intercalation. And that inevitably affects the stress evolution in the material during lithiation versus potassiation and sodiation. So with this, our objective in general in our group is to study the coupling between the electrochemistry and mechanics of these alkali-ion battery electrodes to gain insight about the material strategies to increase capacity, lifetime, and reliability. And the way we want to do this is we are trying to measure the stress and strains in the electrodes in situ and explore the kinetics with the rate-dependent studies and explore the effect of the electrode environments, such as electrolytes, the surface kinetics, and the artificial coatings. And also we look at what is the differences between the intercalation components or the differences between lithium, sodium, or potassium intercalation. So stress measurements are performed by growing or decorating the stiff substrates with the electrodes. So therefore, your electrode is constrained in nature. On the other hand, the strain measurements requires a freestanding electrodes where only one side of the electrode is spot welded for the electrical connection, and the measurements are compiled at the areas where electrode is free to expand in all directions. The way the stress can be measured is using the curvature measurement technique. So it's very straightforward in idea. You are using the laser where the backside of substrate is reflective and also substrate is inert. So it electrochemically and chemically does not react during the operation. when the electrode is lithiated or when the electrode experience a stress, that stress will cause a curvature evolution in the substrates. Therefore, it will change the way the laser is reflects, and you can detect it using the position sensitive detector and use the Stoner equation to convert the experimentally monitored curvature into the integrated stress through the thickness of the film. The beauty of this equation comes from the constants here, where the mechanical properties here as describes the substrates. Since the substrate is inert, these properties are constant. That gives direct correlation between stress and the curvature that's being measured in the experiments. Next is the strain measurements. In this case, we are using digital image correlation technique. So similar to a stress, it's a optical technique. And the left figure here represents the typical surface of the electrodes, where you can observe the randomly distributed speckled patterns on the electrode surface. So what happens as the electrode deforms, the position of the speckled patterns are also changing. And these position changing can be tracked using digital image correlation to calculate the displacements in X and Y directions. The first, we look at the lithium manganese oxide to understand the stress and strain for lithium-ion batteries. So here you are looking at the currents where there are two defined peaks that correlates with the phase transformation in the cathodes. And first, this is from the fourth cycle and very slow rates, 25 microvolt per second. As the lithium is being removed, there is a contraction in the volume where it creates tensile stress if the electrode is constrained by the substrate. And when we lithiate the electrode back by removing the, by reducing the voltage, you see the two redox peaks associated with the, again, from the dilation ones. This time the electrode expands as we expect, and there is a compressed stress generation in the electrodes when it's constrained by the substrate. Very similar to what's the previously done in the graphite, we also observe these localized rate changes in the stress and strain depending on the potential. In a similar idea, look at the, how the strain and stress derivatives evolve during the lithiation and lithiation. If we start from the lithiation, in both cases, the strain derivatives are very well correlated with the lithiation with the current peaks. Same case is stress derivatives. However, during the dilation, we observe asynchronous behavior between stress and strain. The strains are correlated well with the current peaks. However, there is a first initial stress peak evolves before the first phase transformation in the material. To look at a little more, we compare the strain derivatives with the lattice changes in the electrodes. During the lithiation or dilation, the lattice will change due to the lithium insertion or removal. And here the red part represents lattice change from the XRD data, and you observe the reduction in the lattice as the lithium is removed. And these sharp changes in the lattice parameter is well correlated with the stress derivatives. Even what surprised me is the way the derivative works. If you look at here, when there's a large change in the lattice, there's also a sharp strain derivative observed at the same point. So this technique also shows that we can actually monitor these angstrom scale changes in structure by using this micro scale strain technique. However, stress is a different story. Stress can evolve because of simple expansion, or stress might be associated with the surface kinetics. To look at it, we compare the charge transfer resistance changes with the potential, and the charge transfer resistance drops at around when the first stress derivative peak is observed. We also look at the lithiation as I described you later, previously, how the stress and strain affects each other. We came with a concept of electrochemical stiffness. Since the time is short here, I will not have time to discuss it, but The stiffness calculations help us to understand how the stress versus strain actually dominates the mechanical behavior during lithiation process. And we can find more in this previously published paper. The next question is where the surface stress comes from. Is it intrinsically related with the material, which is the lithium manganese oxide in this case, or does it relate with the surface kinetics that might be controlled by the electrolyte or the surface layer decompositions? To explore it, we change the electrodes to lithium iron phosphates. So this electrode only has one phase transformation. And the similar experiments are performed using the same electrolytes, lithium PF6 in ECDMC. Same electrode also used for the graphite and the LMO studies before. Again, there is a one current peak in the LFP because of the one phase transformation. If you look at stress and strain, similarly, we observe expansion and reduction or compressive or tensile stress during lithiation and dilatation. However, what I would like you to look at here is the stress derivative during dilatation. Similar to LMO and graphites, there is an excess stress peak we observe that is onset before the current rise. So before the dilatation literally actually progressed. And the second stress peak is well correlated with the current peak. And the same thing, the current peak is well correlated with the strain derivatives in both sides. So that shows that second derivative and the strain derivative during lithiation and dilatation is actually comes from the changes in the crystal structure. However, there is still a first stress peak evolve at the onset of dilatation. Then we start changing the electrolyte. This time we look at lithium perchloride salts in the same solvents. So one of the main differences here we observe is the changes in the electrochemical response. The current peaks are much narrower, shows the enhancement in the kinetics. And also there is only one derivative peaks in both stress and strain during dilatation and lithiation that correlates very well with the currents. And we observe disappearance of this initial stress peak that we observe in the lithium PF6 salts. We performed the experiments also in the PC solvents, and we observed the solvent did not affect the behavior, but the salt affected. So to further explore, impedance spectroscopy is used to look at the charge transfer resistance of the electrodes at the onset of the lithiation and dilatation in two different salts. In the lithium PF6 one, there is a sharp changes between lithiation and dilatation points. However, the total amount of the resistance change in the lithium perchloride is almost 1-fold smaller. So if you will look at what's really happening is a simple charge transfer resistance problem. So this is from the image from the, I use the review paper. So if you assume this is your LFP or LMO or graphite, your lithium ions need to be generated at the surface reactions. And once they're generated, they need to transfer through the electrolytes, sorry, SEI layer or CEI layer in the cathode surface and form the solvation with the solvents. And that requires the overcoming the energy barrier at the surface that causing the observed stress generation in the particular electrolyte systems. We came with a proposed mechanism of the showing that the lithium PF6 actually decompose more lithium fluorinated or lithium phosphate fluorinated components compared to lithium perchlorides. And when we look at the conductivity values from literature, we found that the conductivity of the SCI components in the lithium PF6 is much, much lower than the conductivity of the SCI components formed in the lithium perchlorides. The next question we look at is what's really happening in the lithium versus sodium intercalation in the material. We know that it changes the crystalline structure, and from the previous studies, there is also a mention about the changing the migration energy compared with the lithium and sodium. To do that, we simply use the electrochemical alkali metal cation displacement methods to to fabricate the sodium iron phosphates. So one thing we observe is the sharp strain evolution in the first cycle, and the strain becomes more reversible at the later cycles in both cases, in lithium and sodium. And as we expect, the sodium causes much larger strains than the lithium. Then we look at the galvanic cycling to look at how the potential hysteresis happen. In lithium iron phosphates, the hysteresis are much lower than the sodium iron phosphates. But what is interesting for us is the strain hysteresis we observe in the lithium iron phosphates. On the other hand, in the sodium intercalation, there is a very nice linear correlation between the strain and the capacity. So we look at the rate dependency of this behavior. So we cycle the electrode at 4 different scan rates, and the strain hysteresis are observed in all scan rates, all fast scan rates in the lithium iron phosphates. However, in all scan rates, the sodium iron phosphates almost show a linear dependency between strain and capacity. When you look at the capacity, it's reduced significantly at faster scan rates for sodium compared to a lithium intercalation. And if you look at the strain change at the state of discharge, you observe that the strain magnitude is increasing at the faster scan rates, and that increase is much greater in the lithiation than the sodiation. In the literature, we know that the lithium intercalation is rate dependent. It's really affect the amount of the active material in the case. And also from the previous dynamic studies, we know that the crystalline lattice changes the migration barrier for the sodium and lithium intercalation. In this case, the lithium intercalation affected more severely with lattice strain compared to a sodium. And even the previous study using the TEM showed that actually a sodiation in this material might cause a amorphization surface to mitigate the mechanical damage in the material. The next step was for us to understand how this stress dependency happened at different scan rates. So previously, the strains are predicted by the elastic properties using the open cell theory and S combining rule. In order to do that, we need to have the XRD data. Thanks to the collaboration with the Montre from Spain, we were able to calculate the composite strain using the changes in the crystal structure. Here, the dots represents the predicted strain, and the straight lines are the experimental strain we have at different scan rates. Or predicted strain correlates very well at the lower range with our slow scan rates. At the higher scan rate, we still observe larger strains experimentally. This model does not include any plasticity and also does not include any localized concentration profiles. So we look at the particle models. The particle strains and stresses previously actually predicted by various groups in early 2000. So I just picked the two group here for the reference. Simply you are using the Fick's law to calculate the concentration profile. And from there, you can use the XRD data to calculate the strains, and also you can use the mechanical properties to calculate the stress profiles.
Ozgur, you have 3 more minutes.
Thank you, Rosie. And when we use our model, we observe that, as expected, there is a large concentration gradients at much faster scan rates in the sodium, and the concentration gradients becomes much narrower at the slower scan rates. When we calculate the misfit strains at these 2 different scan rates, in the particle, again, the particle misfit strains are much greater at faster scan rates compared to slower ones. So that might be associated with what we are observing experimentally, where at faster scan rates, there's a larger expansion in the materials compared to a slower intercalation. So I just want to show you this before we end. We previously showed that the actual coatings might be effective to minimize these expansions at the higher scan rates. In this case, you look at the lithium manganese oxide. Again, the black is the faster, green is the slower scan rates. And when we use the gold or ALD-coated aluminum oxides, we observe a reduction in the volume compared to non-coated sample. And in the last 2 minutes, I want to show you another unpublished data we have. The one question we do have is what happens at the larger ion intercalation. So for the iron phosphate case, so previously Komaba showed that if you try to intercalate potassium in this structure, there will be amorphization. You see the XRD patterns are almost diminished, unlike the sodium and lithium. But in the literature, we know that when we look at the graphite, interestingly, graphite allows potassium and potassium and lithium intercalation, but does not allow sodium to intercalate. And previously, DFT calculation showed that it's not only a pure size effect, but it might be the associated with the formation energies, depending on the components you are forming with lithium, sodium, and potassium. So we look at the strain evolution in the potassium intercalation into iron phosphates. So first of all, you are seeing at the capacity and strain derivatives. We observe a localized changes in strain derivative that actually show that there are some reversible changes during potassium intercalation and the intercalation into iron phosphates. And later, we also cycle it at very slow scan rate, C/25, to look at the effect of lithium, sodium, and potassium in the strains. So here look at the amount of the lithium, sodium, or potassium in the components with the composite strain. And one thing you might realize, the blue and the purple one is the sodium and potassium, and the lines are very close to each other. And the green one is the lithium, where, as we expect, the expansions are much smaller. The same behavior also observed during deletion, dissociation, or depositation. If you look at a little more carefully and closely here, the straight lines are the first, and the dashed lines are here the fourth cycle. We observe that actually the amount of strain during potassium and sodium intercalation is very similar, unlike to what was expected due to the size of the potassium. On the other hand, the lithium has much lower expansions as we expected. So right now we are trying to understand what is limiting the potassium to further intercalate into iron phosphates, and why the strains are very similar in the sodium and potassium. We are working with the PNNL to do some XAS studies to further understand the chemical changes in the structure. So with this, I would like to end my talk here, and thank you again for the organizers for this opportunity, and thank you for your attendance.
Thank you, Ozgur, for the wonderful talk. You have one question there.
Did you use commercial ammo which contains chromium or homemade ammo with additives? We use commercial ammo in the study. We purchased from Sigma.
Okay. Do we have any other questions? So no, okay. Thank you very much for joining us.